So usually when we talk about computer programming, we're operating under this assumption of like absolute granular control.
Right, yeah, completely. You're writing imperative code, so you're essentially micromanaging the control flow.
Exactly. You're dictating the exact sequence of, for loops, managing memory allocation, and
Basically, explicitly telling the processor exactly how to execute every single step just to reach a specific state.
right. You're building a highly sequential machine. The logic is entirely bound to the execution path you define. But then you step into the world of declarative programming, and that entire paradigm just flips.
It really does, because you aren't micromanaging the control flow anymore.
You're defining the logic state itself. Like you're giving the computer a set of facts, right? A set of logical constraints, and then just letting an inference engine do all the heavy lifting to figure out the connection.
Which is such a powerful shift in mindset for a programmer.
It's massive. And today, our mission for this deep dive is to take those abstract logic concepts from your CS330 notes, specifically Class 28 on programming languages and compilers, and look at how they're actually implemented in the real world.
Yeah, we're going to get very hands-on with the theory.
Exactly. We are going to use the web ontology language to solve that famous 5 ships logic puzzle, the Einstein problem, and we're going to do it without writing a single line of traditional step-by-step code.
And this is where we really bridge that gap between abstract theory and applied computer science.
Right.
I mean, you're already familiar with first-order predicate logic from earlier in the course.
Right.
So today, the focus shifts to how we actually build the architecture for a semantic reasoner to traverse that logic. Like, how can a machine parse knowledge, infer missing relationships, and, deduce truths based strictly on the parameters of an ontology?
Well, okay, before we can feed an Einstein problem into a semantic reasoner, I feel like we have to look at the underlying data structure.
For sure. We need a way to store knowledge that a machine can actually traverse.
Right, and according to the lecture notes, that starts with the Resource Description Framework, or RDF. And at the base level, it relies on something called a triple.
A subject, a predicate, and an object.
Exactly. Let's unpack this. It's kind of like diagramming a simple sentence back in elementary school, right? The course material uses a really straightforward example. Anne is the subject, takes class is the predicate, and CS277 is the object.
Yeah, and it's the foundational architecture of the semantic web. When you break down information into an RDF triple like that, you are essentially defining the nodes and edges of a directed graph.
Directed graphs, right.
So the subject is your starting node. The object is your destination node. And the predicate is that directed edge connecting them.
So when you visualize that, it looks exactly like a standard graph database architecture. You have a node for Anne, a node for the class, and a vector mapping the relationship between them.
But the directionality of that vector is the critical mechanical feature here. The arrow only points one way.
Okay, wait, what do you mean?
Well, if you assert a triple, where window is the subject, is the predicate, and glass is the object, the machine registers that specific unidirectional relationship.
Right.
The reasoner does not automatically assume the inverse. It doesn't just look at that graph and deduce that glass is made of window.
Oh, right, because it's operating strictly on the literal edges provided. It's not inferring common sense.
Well, exactly.
But that raises an issue of incomplete data, doesn't it? Because in a real-world knowledge base, you might know a relationship exists, but you totally lack the specific object node to complete the vector.
Oh, like when you know two people have a child, but you don't know the child's name.
Yeah, exactly. Say, we know Anne and Bob have a child together, but the database doesn't have an entry for the child's identity. If an RDF triple requires a subject, predicate, and object to be logically sound...
Which it does.
Right. So how does the graph handle a missing node without just throwing a null pointer exception or like registering the relationship as totally false?
That's a great question. The framework handles this through the use of what they call blank nodes.
Blank nodes, okay.
Yeah, because RDF operates on the principles of first-order logic. A blank node functions as an existential variable.
Right.
So we assert that Anne has a has-child relationship pointing to a blank node. Let's just call it $X.
Okay.
We then assert that Bob has a has-child relationship pointing to that exact same variable, $X.
Oh, I see. It's an anonymous placeholder.
Exactly.
We're basically telling the inference engine that an entity exists that satisfies the specific logical constraints, even if the absolute identifier of that entity is currently, like, unassigned in our graph.
You nailed it. And it preserves the logical soundness of the graph. The reasoner can still perform complex deductions across the network without just failing because it hit an incomplete data structure.
The knowledge base remains truthful.
Exactly.
So RDF gives us the vocabulary, it gives us the nodes and the vectors. We can map out a massive directed graph of relationships. Anne takes CS277 and knows Bob. Bob takes CS277. But a static graph database isn't enough to make a computer actually reason through a logic puzzle. We need to introduce the semantic rules of reality.
And that's where OWL comes in.
OWL, yeah, the web ontology language.
Because RDF is really just data storage, right? OWL provides the actual semantic layer. It gives us the formal grammar to define the nature of the properties themselves.
So we use OWL to build an ontology, which basically dictates the types, properties, and interrelationships within a specific logical domain.
Right. And the notes highlight this massive philosophical difference in how OWL reasoners approach data compared to, like, standard SQL databases.
Oh, yeah. This part is fascinating. Traditional databases operate on a closed world assumption.
Yes. They use negation as failure.
Right. So if a database doesn't explicitly contain a record saying you have a driver's license, the system inherently assumes you do not have one.
Exactly. But OWL reasoners generally operate on an open world assumption, and this is a fundamental paradigm shift for a lot of programming.
Okay, so how does that work?
In an open world assumption, the absence of a fact does not imply falsity. The machine just assumes its knowledge of the graph is incomplete.
Wait, really? So anything not explicitly defined as false could technically be true?
Exactly.
Okay, here's where it gets really interesting to me. If the reasoner assumes incomplete knowledge and allows for any unnegated possibility, doesn't that introduce a major risk of, like, conflating distinct entities?
What do you mean?
Well, the notes mention those two courses, CS277 and MA270. If the machine assumes anything is possible and sees two nodes with similar properties, like maybe they share the same professor node and the same classroom node, couldn't an open world reasoner just deduce that CS277 and MA270 are just two different URIs referencing the exact same object in memory?
Oh, absolutely. The reasoner will completely collapse those two nodes into one if you don't explicitly restrict it.
Wow. Okay.
Yeah. So to maintain distinct memory spaces in the semantic graph, we have to enforce individual identity. We use an OWL property called owl.differentFrom.
Right.
So we write a rule asserting that the node CS277 is logically distinct from the node MA270.
But wait, if you're building an ontology with a large set of distinct variables, manually writing bilateral different from rules for every single combination, I mean, that would be a highly inefficient use of code.
Oh, it would be a nightmare. Which is why the language provides OWL, all different.
Oh, okay.
Yeah, you just supply a set of individuals, say Anne, Bob, Carl, Dan, and the reasoner automatically maps mutually exclusive boundaries between all of them simultaneously.
Okay, so establishing those boundaries prevents the graph from collapsing. But the real computational power of OWL, at least to me, comes from how it generates new logic paths.
Yes.
The course outlines these specific properties we can apply to our predicates to trigger automated inference. Like, let's look at owl.inverso.
Sure. So we established earlier that RDF vectors are unidirectional, right?
Right.
If node A points to node B with a has-parent edge, the machine doesn't inherently know that B has child A.
Because it's a one-way arrow.
Exactly. But by defining has-child as the owl.inverse off has-parent in our ontology, we actually change the rules of the engine itself.
Oh, wow.
Yeah. The moment you feed the reasoner the fact A has parent B, it dynamically writes the reciprocal edge into the graph.
It automatically generates new knowledge. And
Yeah.
you didn't have to write, like, an imperative loop to parse and update the database.
Not a single line. And the same mechanism applies to OWL symmetric property.
Right.
If you define knows as symmetric and assert that Anne knows Bob, the engine immediately generates the vector Bob knows Anne. The relationship becomes computationally bidirectional.
That is so cool. But the property that really expands the graph, though, is the OWL transitive property.
Oh, definitely.
This is where you see the real cascade effect of declarative programming. If we define learned from as a transitive property, and the graph contains the edge, A learned from B, another edge, B learned from C.
The reasoner bypasses the intermediate node.
Exactly. It automatically deduces and writes a direct vector asserting that A learned from C.
It's wild. You're basically watching the machine build logical shortcuts across its own architecture.
Yeah.
This is how a semantic reasoner traverses a graph. It uses these definitions, transitive chains, symmetric reflections, inverse reciprocals, to populate all the empty spaces in the knowledge base.
Which brings us to the ultimate application of this class session. actually solving the Einstein problem.
The 5 ships logic puzzle.
Right. So we have this scenario with 5 ships docked in a port. And each ship has 5 distinct variables, right? It operates under a different country's flag, it has a different colored chimney, it carries a different cargo, it's heading to a different destination, and it departs at a different time.
So that defines our parameters. We have a matrix of 25 unknown variables distributed across 5 entities.
And the puzzle gives you exactly 15 disparate facts. Things like the Greek ship carries coffee, or the ship in the middle has a black chimney. The French ship with a blue chimney is immediately left of a ship carrying coffee. And from just those 15 constraints, you have to deduce 2 final answers. Which ship goes to port side, and which ship carries tea?
Now, if you were tasked with writing a standard C or Java program to solve this, the logic would be exhaustive.
Oh, it would be awful.
You'd need nested iterations checking every possible combination of variables against the 15 constraints, utilizing constant state checking, backtracking algorithms.
But implementing this via OWL requires a completely different mechanism, doesn't it?
Completely. We aren't writing algorithms to search for the answer. We are constructing an environment where only the correct answer can logically exist.
That is such a profound way to phrase it.
Well, we begin by enforcing a closed world within our OWL ontology. We use that OWL, all different property we talked about, to assert that there are exactly 5 ship nodes and that they're mutually exclusive.
Okay, so we're locking it down.
Exactly. We do the same for the 5 flags, the 5 colors, the 5 cargoes. We are restricting the domains and ranges of our properties so the inference engine cannot hallucinate external variables.
Okay, and then we map the relational properties. Like, we take a concept like immediately left of and define its OWL inverse of as immediately right of.
Yes.
And we could define a broader property like is to the left of as an OWL transitive property.
Precisely. And once the semantic framework is strictly defined like that, we just feed the 15 known facts into the system as RDF triples.
Like a detective dropping 15 distinct clues onto a corkboard.
Yeah, that's a great analogy. And here is where the mechanism of the semantic reasoner just takes over. It doesn't run a sequential search. It executes a constraint satisfaction algorithm across the entire semantic graph.
So it looks at the graph it's been given. It sees a node for the French ship with an edge pointing to a blue chimney, and it sees the rule stating the French ship is immediately left of the ship carrying coffee.
Right, and using the inverse property we defined, it simultaneously deduces the coffee ship is immediately right of the French ship.
And it applies those all different constraints to prune invalid branches of the graph, right? Like if fact 3 says the ship in the middle has a black chimney, the reasoner knows the French ship has a blue chimney.
Exactly. Therefore, due to the mutual exclusivity rules, it totally eliminates the possibility of the French ship occupying the middle position.
So it's just chaining these transitive and inverse deductions, cross-referencing them against the restrictive bounds of the ontology.
Right. It resolves the logic paths, collapsing the possibilities until every node strictly satisfies every constraint. It continually maps the graph until only one valid state remains.
And it arrives at that state instantly. It deduces the exact path to port side and the exact location of the tea cargo.
It's amazing to see.
The lecture notes suggest running this through a visualization tool like WebVOWL. And when you do that, you aren't looking at lines of code. You're looking at a topographical map of logic.
Yeah, you can physically see the nodes of the graph.
Yeah, and you watch how the inference engine has drawn these strict, unassailable vectors connecting the French ship to its specific cargo based purely on the cascading rules of your ontology.
It is a profound demonstration of the difference between computing an operation and evaluating a state of truth.
Definitely.
You defined the parameters of reality, and the machine reasoned its way to the only mathematically viable conclusion.
And, the rigor required to build an OWL ontology that doesn't just collapse on itself, defining strict domains, enforcing ranges, and resolving types, that maps perfectly to the precision you need for the imperative projects you're building in CS330 right now.
Oh, absolutely. While we're discussing the automated logic of declarative programming today, your syllabus demands a very manual, hands-on application of type checking and logical precision.
Which is a perfect segue. The theories discussed in Class 28 only matter if you actually execute on the deliverables. So let's align on the course schedule real quick.
Good idea.
Today is Wednesday, April 29th. Just to establish the timeline, last week required the submission of Lab 11, that was the closure assignment, as well as your Week 13 journal entry.
Right. And following that, just this past Monday, April 27th, Lab 10, Part 1 was due. That was the first half of the B minor compiler.
Which brings us to the immediate deadline. Today, Wednesday, April 29th, is the deadline for Lab 10, Part 2, the B minor program.
Get it in, guys.
Seriously, the strict semantic rules we just discussed regarding how a compiler interprets definitions and distinct variables, that should be top of mind as you finalize this submission.
Definitely. And moving into the final stretch of the semester, next Monday, May 4th, is critical.
Huge day.
Your final exam will be administered at 9:00 a.m. sharp. That's in the Linux lab, room BTCIS 237.
Also due on Monday the 4th is the Lab 10 extra credit. And the syllabus is highly specific on this point, okay? You must explicitly document the extra credit features you implemented inside your readme.md file.
Yes. If the features are not listed in the readme, the compiler will not magically deduce their existence.
Right. There is no semantic reasoner to save you here. You will not receive the points.
So be explicit with your documentation. And finally, the absolute last deliverable for the course is Wednesday, May 6th, which is when your final journal entry is due.
Awesome. So wrapping up, today's deep dive really traced the whole architecture of declarative programming. We started with the foundational data structure of the RDF triple subject, predicate, object, and saw how it forms the directed edges of a graph database.
Right.
Then we explored the semantic layer of OWL, examining how the open world assumption radically alters how a machine processes incomplete knowledge.
Which is a massive shift.
It really is.
Yeah.
We saw how properties like inverse and transitive definitions allow a semantic reasoner to generate new logic vectors automatically, and we watched that mechanism execute constraint satisfaction to instantly resolve the 25 variables of the 5 ships puzzle.
And it really is the evolution of data, from static storage to defined knowledge to automated reasoning.
So, as you prepare for your final exam, I really want you to consider how this paradigm shift impacts your broader approach to computer science. When you face a complex architecture problem in the future, how does shifting your mindset from imperative control dictating exactly how a machine must loop through memory to declarative definition, establishing what constraints are true, change your fundamental approach to logic design?
That's a great question. And, beyond local programming, consider the macro application of these frameworks.
Yeah.
The semantic rules we use to solve a 15-fact puzzle, they're the exact same rules governing the linked open data cloud.
Oh, wow. The LOD cloud.
Yeah. We are talking about billions of RDF triples utilizing OWL to map vast, disparate data sets from global governments, life sciences, geographic systems, and linguistic databases.
That's scale on another level.
It's an attempt to structure the entire internet into a single traversable graph. So if an inference engine can cascade transitive properties to instantly deduce hidden truths about a French ship and its cargo, what hidden connections, what world-altering insights are currently embedded in the linked open data cloud, just waiting for a semantic reasoner powerful enough to deduce them?
The facts are already mapped. We just need to define the ontology that brings them to light. Good luck on the B minor program today, and good luck on the final exam next week.